Hi, welcome to the semantics lecture about object quantifiers. Object quantifiers are going to mess our stuff up simply because they don't compose the way we want them to. We'll take a simple example. Elena hugged every kitten. Straightforward sentence, straightforward syntax. Looks pretty easy, but when we try to compose everything, it all goes awry. Why? Well, let's say we have hugged, which is of type E, E, T. This will give us 1 or 0. And then we have our DP, every kitten, which we've already built up to the DP level. And this is type ETT, right? You give it a property, and it will give you 1 if every kitten has that property, and 0 if it's not the case that every kitten has that property. So when we try to combine them, we can't, right? This requires something of type E. That's not enough to cut it. This is of type EET, and it won't fit here. So neither of these will fit, and that's going to be a problem that we'll have to solve. And we can't solve it just by looking at this, right? But we can solve it if we look at the nature of quantifiers when they interact with each other. So now let's look at another fact that will help us understand what we need to do to fix the object quantifier problem. So let's look at this sentence. A lady hugged every cat. This has a straightforward syntax. We'd say it has surface scope if there is a lady such that that lady hugged every cat. But we can also get that sentence, a lady hugged every cat, to have an inverse scope reading. So in that case, every cat is such that it was hugged by a lady. We can get that overtly through passivization, like we have here. But we can just get a simple inverse scope reading of this sentence, and then we want to ask ourselves, well, if this sentence can have the scope that this sentence has, how? Now for Montague, there wasn't really an issue for that because of the way he defined referential expressions and consequently verbs, so it worked out pretty simply. But if we're looking at something where the verb takes 2 entities, we have an issue. Now, we have that fact. We also have different kinds of scope rigidity facts in a lot of languages. So in a language like Turkish, the sentence that most students read every book, where most students take scope over every book, will have to be with this structure, where most students, öğrencilerin çoğu, take scope over her kitab, more every book. And then if you want the opposite reading, the inverse scope reading, then you have to literally invert the subject and the object. Now the case marking will tell you who's doing what, and so that part of the sentence doesn't change, but what changes is that these sentences don't mean the same thing. This means that most students are such that they read every book, so most of the students read every book. And in this case, every book is such that most students read it. So in this case, we get a slightly different reading. And we have this fact that tells us that you can get different scope facts by actually restructuring the sentence, just like you do here. So what's going on here? Well, the thought was, through the 60s and into the 70s, that, well, perhaps some kind of transformation would transform this into a sentence, but it wasn't clear where that transformation would apply. And in that case, once transformation stopped being used anyways, it became a bit moot. But if we're thinking about a movement analysis, where we build structures and then move things in order to build new structures, then we have to ask ourselves, well, how do we get this structure to have this structure? And the simple answer is through movement. Now, the only thing is that we don't have movement, right? We have every cat leaving a trace behind, and moving up here, well, that would give us the scope. That would say every cat is such that a lady hugged it. That works, but we don't have that. We don't have that movement like we have, let's say, in Turkish. So what we ended up doing is proposing that based on how the grammar works, where the grammar is built with a syntax, then it's spelled out to the PF and the LF, that we get the movement occurring at LF, but not at PF. So when we're building these syntactic structures right here in the syntax, then that, the result of that will get fed to the PF and get pronounced. That same result gets fed to the LF. But we can have more syntactic processes occur just at LF. And one of these is the movement of a quantifier into the right scope position. Since it involves raising of a quantifier, we call this movement quantifier raising. And this is a type of movement that happens at LF, so it happens after the PF has been fed. So we don't see it at PF. It doesn't occur overtly. It occurs covertly. And we end up with a kind of movement that tells us something about the way the grammar is worked, the way the grammar is built. And a number of semanticists and even some syntacticians have been suspicious of this notion of quantifier movement or quantifier raising, but it turns out that QR is very useful in a number of different phenomena, from antecedent contained deletion and other ellipsis facts, intervention effects, comparatives, correlatives, and all sorts of phenomena that make a lot more sense if we accept the notion that movement syntactic operations can happen inside the LF. And since they happen at LF, they will feed the semantics. So the semantics doesn't see this movement. It'll just see the structure that results. So we get every cat, a lady hugged, T of 1, and then T sub 1. And so now we have a trace and we can start interpreting. So we've seen that if we move a quantifier at LF, we can get the right result. And we end up with a syntax that looks like this. Every kitten, a lady hugged, T sub 1. Now this has an index. And of course, we usually link it to the moved phrase via an index as well. But we're not going to be able to do that quite so easily in the semantics, because what we're going to do is move this out. This will build a sentence of type T. But remember, we need this to be of type ET to plug into every kitten, which is of type ETT. So we're going to have to bind this variable, and that's really what the useful step is going to be. We bind this variable, we create a property. What property? Well, the property of there being a lady who hugged you. And what we're going to say is that everything that has the property of being a kitten also has that property. But in order to create a property, we need to abstract, and in order to abstract, we need to bind. And so we'll put the binder as the sister to this sentence, as opposed to putting it directly onto the kitten. Now, Heim and Kratzer discuss in a bit more detail why this makes sense semantically, and they point out that there aren't really any syntactic consequences. Worst case, we need a head at this spot. But in their notions of movements that require a feature-bearing head to trigger movement to a specifier position, well then maybe that's what that head is. It's just a binding index. So we have an index, and it will bind it, and this will create our property. And then we can work our way up the tree. So T sub 1 is going to be interpreted. Let's use assignment G just because it's a good assignment. And that's going to be interpreted with the pronoun rule. Hugged, we know, it's lambda x in D sub E, lambda y in D sub E, hugged xy, and that's lexical terminal rule, EET. Okay, and now we're going to combine that, and then we'll see how it fits with a lady. Alright, so there is a y such that y is a lady and y hooked to G of 1, and we can get that through reduction. We'll do that in just a second here. Now here is where we run into the issue. This is of type T, and it's a sentence, right? We need to convert that into a property that we can plug into every kitten. Right? And recall, every kitten is going to look like this. It takes a property of type ET, and it says that for all x, such that x is a kitten, then x has the property of G. And that will come about through functional application of type ETT. So this is every kitten. We need to get from here to there, and so we use predicate abstraction. So we'll have a binder, and since we have a binder and an expression, we can abstract over it. So remember the steps for predicate abstraction. You add an argument, step 1. You copy the condition, that's step 2. Then you modify the assignment, that's step 3. And remember, you modify it so that this index points to this variable. And then, step 4, you plug it in. G such that 1 maps to x of 1 will map to 1. And so we get x. Alright, and that we can use predicate abstraction, and that is type ET. Now we can plug this in to kitten. And then we can do that, and this will be a multi-step process as well. Right, so the first step, we plug this in to here, that's our G, right? And then we get rid of that. So now we have, for all x, if x is a kitten, then x will have this property. Now we have a function argument structure, we can reduce that. Our final outcome. Everything that is a kitten, for everything there is a kitten, there is a thing that is a lady, such that the lady hugged the kitten. And that is exactly what we want. And this gets us our scope fact as well. So notice that there is a lady is in the scope of every kitten. And that's essentially how the scope works. The scope works because we have bound a variable inside this constituent and plugged it in as a function to this one. And by doing those two things, we end up creating a scope distinction. So now we have our scope fact, and this is the result we want. So by moving every kitten at LF through the process of QR, we create the right structure that gives us the right scope fact that we want. And we don't see this movement because it happens after spell out, but it has a very clear effect on the semantics, and so we can work our way to understanding how sentences with object quantifiers can be interpreted. So now that we've seen how the QR works, we'll be able to plug it into, we'll be able to apply it even when we don't really need it for scope facts. We can still use it for the type facts. So coming back to Elena hugged every kitten, our LF is not going to look like this. It's going to look like this, where we've moved every kitten and left it traced behind. So we add the binder, we always add the binder, and we have every kitten as our DP, and then we can give this a label. Now this is going to move essentially as far up as it needs to. In this case it moves to here, but we'll see that as essentially has to go beyond the subject. So wherever the subject's going to be, that's where QR is going to take you. So now we can rewrite this sentence so that it no longer has the quantifier as the object of the verb, but a trace. Let's again assume that we have assignment G, and based on the pronoun rule, that will be of type E. Well, this we can plug in, and we can build our way up to sentence level. And we'll do that right now. Okay, so now we have our sentence. This is S. This is hugged G1 of 1 Elena. So Elena hugged G of 1. Who is G of 1? Well, it's going to be whatever the kitten is. Remember that the truth conditions are for every kitten is such that Elena hugged it. Well, this G of 1 is going to be that it. But it's not going to depend, its meaning won't depend on the assignment. Instead, it's going to depend on the quantifier, the binder. So we need to bind it. And that's where predicate abstraction comes in. So we can, again, well, we'll move it over here. We'll show you how this works, right? We add the property, then we copy the value, then we modify the value so that the index maps to the variable, and then we plug it in. And we get lambda x hugged x Elena, the property of being hugged by Elena. Now, we can plug that property into every kitten. Right? Every kitten is the set of properties that every kitten has. So what we're going to say is that the property of being hugged by Elena is a property that every kitten has. We plug that into every kitten, which we had before, and so we'll write it like this. Right, every took kitten as its argument. We plug that in, and we'll get the result. And the x, we'll get the result for every x such that x is a kitten. Then the property of being hugged by Elena applies to it. And then we can reduce that, right? We reduce that to and so we get our result. This is functional application type T. Every x is such that if it is a kitten, Elena hugged it. And I messed that one up. Alright, there we go. Everything is such that if it is a kitten, Elena hugged it. Right? And this gives us the right truth conditions for this sentence. So we had to QR it anyways. Although it didn't make a difference for scope, it does make a difference if we want the truth conditions to work. And that is how we do object quantification. We have to add this step to the grammar that affects the way that our syntax gets built. But the QR that we introduced here is going to be a very powerful tool for lots of other phenomena throughout language and in the syntax and the syntax-semantics interface. So it's a tool we're going to keep using, or a tool we're going to master, and we will continue doing quantifiers.